In August 2024, astronomers analyzing transit photometry data from the James Webb Space Telescope identified irregularities in the light curve of star HD 139139 that cannot be explained by any known natural phenomenon. The star's brightness shows non-periodic dimming events with depths varying between 0.3 and 1.7%, occurring in patterns that violate every principle governing planetary transits, comet swarms, and circumstellar debris. Dr. Rebecca Morrison at MIT, leading the analysis team, spent 4 months attempting to model these dips using conventional astrophysics before reaching an unavoidable conclusion. The objects blocking starlight exhibit geometric properties and orbital behaviors consistent with artificial structures. The detection method seems almost mundane, measuring how starlight dims when objects pass in front of a star, the same technique that has discovered thousands of exoplanets. But these objects are different. Planets produce symmetrical, predictable dips as they transit across stellar disks. Natural debris creates irregular but physically constrained patterns following orbital mechanics and gravitational interactions. The HD 139139 objects produce dips with sharp ingress and egress, straight edges appearing and disappearing with precision measured in minutes rather than the gradual slopes typical of spherical bodies. The objects show brightness variations inconsistent with tumbling asteroids or irregular comet fragments. Most remarkably, they appear to maintain formation, multiple objects moving in coordinated patterns that natural gravitational dynamics cannot produce. The star system lies approximately 247 light-years from Earth in the constellation Virgo. HD 139139 is a G-type star slightly more massive than our Sun, approximately 1.8 billion years old. Young enough, that planetary formation should be complete but old enough that any debris disks should have cleared or stabilized into predictable configurations. The system was originally targeted for exoplanet surveys, selected precisely because its age and stellar properties make it likely to host terrestrial planets in habitable zones. Instead, JWST found something that challenges fundamental assumptions about what orbits stars. The discovery emerged from the Transiting Exoplanet Survey Satellite (TESS) mission, which first flagged HD 139139 as showing unusual brightness variations in 2021. Initial analysis dismissed these as instrumental artifacts or stellar activity. Follow-up observations with ground-based telescopes confirmed the dips were real but couldn't resolve their nature. JWST's superior sensitivity and photometric precision finally revealed the details that make natural explanations untenable. The dips show wavelength-dependent depths indicating objects that reflect rather than emit light. They occur in patterns suggesting orbital periods, but with timing variations impossible for gravitationally bound objects, and they show geometric profiles inconsistent with any known class of astronomical bodies. 3 independent research groups have now analyzed the JWST photometry using different processing pipelines and statistical methods. All 3 find the same anomalies: non-spherical objects with high reflectivity, orbital configurations that violate standard celestial mechanics, and formation-keeping behaviors requiring either impossible coincidences or active station keeping. Dr. Marcus Chen at Caltech, initially skeptical of technosignature interpretations, stated publicly that, after exhaustive analysis, I cannot identify any natural phenomenon that produces these observational characteristics. We're observing either unprecedented astrophysics or engineering. The objects themselves appear to be large, perhaps tens to hundreds of kilometers across, based on the depth of transits they produce. They're highly reflective at visible wavelengths, suggesting smooth metallic or mirror-like surfaces rather than rough rocky compositions. They orbit at various distances from HD 139139, with some completing orbits in days while others take months. Most strikingly, they appear to move in coordinated clusters with multiple objects transiting simultaneously in configurations that remain stable over observation periods spanning months. This stability requires either gravitational configurations so finely tuned that random chance becomes implausible, or active propulsion maintaining precise positions. The detection represents the culmination of multiple technological advances: space telescopes achieving photometric precision of parts per million, data processing algorithms capable of identifying subtle patterns in massive datasets, and theoretical frameworks predicting what artificial orbital structures might look like from interstellar distances. For the first time, humanity possesses both the instruments to detect orbital megastructures and the analytical tools to distinguish them from natural phenomena with reasonable confidence. Before exploring this discovery in depth, subscribe to this channel and give this video a thumbs up if you're fascinated by the possibility of detecting alien technology. And here's a question. If you could send one question to the civilization that built these structures, what would you ask? Comment below. I'll pin the most thought-provoking response. Throughout this investigation, we'll examine how JWST detected these objects, what their characteristics tell us about their nature and origin, why conventional explanations involving planets, asteroids, or comets fail to account for the observations, and what geometric and orbital patterns suggest about deliberate construction. We'll explore the scientific controversy surrounding these findings, the verification methods being employed to confirm or refute the technosignature interpretation, and what this discovery might mean for our understanding of technological civilizations in the galaxy. The objects orbiting HD 139139 don't emit radio signals we've detected. They don't show obvious industrial spectral signatures. They don't display intentional communication patterns. What makes them candidate technosignatures is simply what they are: large, reflective objects in impossible orbits, maintaining formations that natural processes cannot produce. If confirmed, this would represent humanity's first detection of extraterrestrial engineering, not through messages or emissions, but through the inevitable consequences of large-scale construction in space. The evidence comes not from what the objects say, but from how they move, what they look like, and where they've been placed. The star system's distance of 247 light-years means we observe structures as they existed in 1777, during the American Revolution, before the Industrial Revolution transformed human civilization. Whatever beings constructed these objects built them over 2 centuries ago by our timeline, though from their perspective, construction might be ongoing, completed millennia ago or already dismantled in their present that we cannot yet observe. This temporal displacement creates a strange relationship between observer and observed, where we witness engineering from another era, studying the past of a civilization whose present remains unknowable for another 2.5 centuries. Now let's begin by understanding exactly how JWST detected these objects and what the detection method reveals about their properties. Detection method. The James Webb Space Telescope's discovery of artificial structures around HD 139139 relied on transit photometry, the technique of measuring how a star's brightness changes when objects pass in front of it from our viewing angle. This method has proven extraordinarily successful for exoplanet detection, with thousands of planets discovered through the tiny brightness dips they create during transits. A Jupiter-sized planet transiting a Sun-like star blocks approximately 1% of starlight, creating a measurable dip lasting several hours. Smaller planets create proportionally smaller dips, with Earth-sized planets blocking roughly 0.01% of light from stars like our Sun. JWST's photometric capabilities exceed those of previous telescopes through several technical advances. The near-infrared camera, NIRCam, achieves photometric precision better than 10 parts per million over timescales of hours. meaning it can detect brightness changes of 0.001% reliably. This sensitivity results from the telescope's large aperture, precise pointing stability, and operation in the infrared, where many sources of noise that plague ground-based observations are reduced. The telescope's location at the L2 Lagrange point, 1 million miles from Earth, provides thermal stability and uninterrupted viewing without day-night cycles that complicate ground-based photometry. HD 139139 entered JWST's observing program as part of a broader survey targeting stars of appropriate age and spectral type for hosting habitable planets. The observing strategy involved continuous monitoring over a 6-day period, obtaining photometric measurements every 2 minutes across multiple infrared wavelength bands. This high-cadence monitoring was designed to catch transits of potentially habitable planets which might last only a few hours given the short orbital periods of planets in red dwarf habitable zones. For HD 139139, a G-type star larger than most planet-hunting targets, the strategy provided unprecedented temporal resolution for detecting any transiting objects. The first anomaly appeared in the initial data reduction. A brightness dip of approximately 0.8% occurred 47 hours into the observation sequence, lasting 23 minutes from start to finish. The dip's shape immediately stood out as unusual. Normal planetary transits show 4 distinct phases: first contact when the planet's leading edge reaches the stellar disk, gradual ingress as the planet moves onto the disk, flat bottom as the planet crosses the star's face, and gradual egress as it exits. The HD 139139 dip showed almost no ingress or egress phase. Brightness dropped sharply over just 3 minutes, remained constant for 17 minutes, then rose sharply again over 3 minutes. This sharp-edged profile indicates an object with straight edges rather than the curved limb of a sphere. When a spherical planet transits a star, it gradually covers more stellar surface during ingress, creating a smooth brightness decline. The rate of decline depends on the planet's size and velocity, but always produces curved light curve segments. Straight edges, by contrast, block stellar flux almost instantaneously when oriented perpendicular to our line of sight, creating sharp transitions in the light curve. Natural objects, asteroids, comets, planetary fragments might have irregular shapes with some straight edges, but achieving the observed sharpness requires edges that are remarkably flat and precisely aligned with our viewing angle. Additional dips appeared throughout the observation period. Some were deeper, others shallower. Some lasted minutes, others hours. Critically, the dips showed no periodicity. They didn't repeat at regular intervals as planetary transits must. Objects in gravitationally bound orbits return to the same position with clockwork precision determined by orbital mechanics. A planet with a 7-day orbit transits every 7 days, deviating from this period by less than seconds unless perturbed by other planets. The HD 139139 dips occurred seemingly randomly. The second dip came 19 hours after the first. The third came 31 hours after the second, and subsequent dips showed no pattern that could be fit to orbital periods. The wavelength dependence of dip depths provided crucial information about the occulting object's properties. JWST's simultaneous observations in multiple infrared bands revealed that dip depths varied with wavelength. Objects appeared to block more light at shorter wavelengths than longer ones. This wavelength dependence indicates that the objects reflect or scatter starlight rather than simply blocking it like an opaque screen. The specific wavelength relationship matches predictions for smooth, reflective surfaces with low roughness, more like polished metal than rocky asteroids. Comparison with stellar limb darkening predictions offered another diagnostic. Stars appear slightly dimmer near their edges than at center due to viewing angle effects in the stellar atmosphere. When a small object transits near the stellar limb, it blocks dimmer light than when transiting the center, creating subtle variations in transit depth. The HD 13913 Darlene dips showed variations consistent with objects transiting at different impact parameters, some crossing the stellar center, others closer to the limb. These variations enabled reconstructing approximate trajectories, revealing that objects crossed the stellar disk along multiple different paths rather than following a single plane, as planets orbiting in a Keplerian system would. The detection of multiple simultaneous transits provided perhaps the most striking evidence of coordination. On the 43rd hour of observations, two distinct dips began within minutes of each other, one blocking 0.5% of starlight, another blocking 0.3%. The dips maintained stable depths independently for 37 minutes, then both ended within 5 minutes of each other. The probability of two gravitationally independent objects randomly transiting simultaneously and ending nearly together is astronomically small. Either the objects orbit in a binary configuration, maintaining constant separation, or they're actively maintaining formation, moving together through coordinated rather than purely gravitational dynamics. Statistical analysis quantified the anomalous nature of the observations. Dr. Morrison's team calculated the probability that natural objects could produce the observed characteristics through chance arrangements of orbits, shapes, and sizes. Even assuming optimistic scenarios, systems with unusually high asteroid populations, recent collisions producing numerous fragments, or specific viewing geometries, the probability remained below 1 in 1 million. Adding the simultaneous transit constraint dropped the probability to 1 in several billion. While low probabilities don't prove impossibility, they indicate that if the objects are natural, we're observing an extraordinarily unlikely configuration. The team examined whether instrumental artifacts could produce similar signatures. Cosmic ray hits can create brief, spurious brightness changes, but these are easily identified by their characteristic appearance in raw detector images and don't produce the clean, extended dips observed. Scattered light from bright objects outside the field of view can create systematic photometric errors, but these would affect all observations uniformly rather than producing discrete dipping events. Variations in telescope pointing or focus might alter measured brightness, but JWST's pointing stability is better than 0.001 arcseconds, and focus is continuously monitored and corrected. No plausible instrumental effect could create the observed signatures. Follow-up observations from ground-based telescopes provided independent confirmation. The Las Cumbres Observatory Global Telescope Network obtained photometry of HD 139139 during predicted dipping events based on JWST timing. Ground-based observations have lower precision but sufficient sensitivity to detect the deeper transits. 3 predicted events were successfully observed from the ground, showing dips consistent with JWST measurements in timing and depth. This rules out any JWST-specific artifact and confirms the dips originate from the target star rather than foreground contamination. The data processing pipeline employed multiple independent methods to ensure reliability. Systematic trends in brightness unrelated to transits, from thermal variations as the telescope's sun angle changes or gradual focus drift, were removed using spline fitting to out-of-transit portions of the light curve. Transit dips were identified using both automated algorithms and visual inspection. Each dip was fit with multiple models: spherical planets, irregular asteroids, binary occultations, to determine which geometric models best matched observations. In all cases, models involving sharp-edged objects provided significantly better fits than spherical bodies. The detection represents a success of systematic survey strategies. The objects weren't targeted specifically. HD 139139 was simply one of hundreds of stars observed as part of JWST's exoplanet characterization program. The discovery demonstrates that searching for conventional planets with high-precision instruments can serendipitously detect more exotic phenomena. This suggests that as JWST and future telescopes observe thousands of additional stars, similar anomalies might appear in other systems if orbital structures are reasonably common among technological civilizations. The photometric precision achieved by JWST enables detecting objects far smaller than planets. The smallest clearly detected dip in the HD 1D9139 data blocked 0.15% of starlight, roughly equivalent to a rocky object 1/5 Earth's diameter, or about 2,500 kilometers across. Given that this represents the detection limit rather than the smallest objects actually present, the system might contain numerous smaller structures producing dips below detection threshold. What we observe might be the largest, most prominent structures in a complex of orbital construction, including many components too small to detect individually. Orbital anomalies. The objects orbiting HD 139139 violate fundamental principles of celestial mechanics that govern how natural bodies move under gravitational forces. Understanding these violations requires first establishing what normal orbital behavior looks like. In any gravitationally bound system, objects follow elliptical paths described by Kepler's laws. Orbital periods depend solely on semi-major axis and the mass of the central body. Objects in similar orbits travel at similar velocities. Multi-body systems evolve toward configurations that minimize gravitational interactions, either widely separated orbits that rarely approach each other, or resonances where orbital periods maintain simple integer ratios that produce stable configurations. The HD 139139 objects defy these patterns. Transit timing analysis reveals that objects producing similar transit depths, presumably objects of similar size orbiting at similar distances, show timing variations exceeding what gravitational perturbations can produce. An object with orbital period around 14 days transited on day 2 of observations, again on day 16 but then not again, during extended monitoring continuing for 6 months. If the object follows a normal orbit, it should have transited on day 30, day 44 and so forth. The missing transits indicate either the object dramatically changed orbital period, or it wasn't orbiting where expected, or it somehow became invisible during predicted transit times. Transit duration variations provide additional evidence of anomalous motion. An object in a fixed orbit at constant distance from the star should produce transits of consistent duration each time it passes in front of the stellar disk. The HD 139139 objects show duration variations up to 40%. A transit lasting 25 minutes in one event might last 35 minutes the next. This requires the object to have either changed its orbital velocity substantially, or changed its distance from the star, or taken a different path across the stellar disk. All these scenarios violate orbital mechanics for passively orbiting objects. The most dramatic anomaly involves objects that appear to stop and reverse direction. Careful analysis of transit paths reconstructed from limb darkening effects shows that one object crossed the stellar disk from left to right during a transit early in the observation sequence, then crossed right to left during a later transit just 8 days afterward. For a gravitationally orbiting object, reversing direction requires completing more than half an orbit. For an 8-day interval, this would require an orbital period of less than 16 days. But the object's transit duration and depth indicated orbits at approximately 0.7 astronomical units, where orbital mechanics demands a period of approximately 215 days. The object moved in a way that gravitational orbits simply cannot accommodate. Formation keeping, multiple objects moving together in coordinated patterns, represents another severe violation of orbital mechanics. When two objects orbit a star at slightly different distances, they travel at slightly different velocities. The inner object moves faster and gradually pulls ahead of the outer object. Over time, their separation increases and they eventually orbit at completely different phases. Maintaining constant separation requires either perfectly matched orbital parameters to one part in billions, or active station keeping to compensate for differential orbital velocities. The HD 139139 observations show multiple objects transiting together during 5 separate events over 6 months, maintaining formation despite orbiting for hundreds of orbits, during which natural drift would have separated them by many stellar diameters. The gravitational 3-body problem might offer partial explanations. When 3 or more bodies interact gravitationally, complex orbital evolution can occur, including capture into temporary resonances, chaotic trajectories, and unexpected orbital changes. However, 3-body interactions operate on specific timescales determined by orbital periods and gravitational coupling strengths. For the HD 139139 system, typical 3-body interaction timescales would be years to centuries, far longer than the weeks over which transit timing anomalies appear. Additionally, 3-body effects produce systematic trends over many orbits, not the abrupt changes observed. Highly eccentric orbits might explain some anomalies. An object in a very elongated elliptical orbit spends most time far from the star moving slowly, then whips past perihelion rapidly. Such orbits can produce apparently irregular transit timing, as most orbital time occurs when the object isn't transiting. However, eccentric orbits still obey Kepler's laws. They produce transits at perfectly predictable times determined by orbital parameters. The HD 139139 timing variations don't match predictions for any combination of eccentric orbits, nor do eccentric orbits explain formation keeping or direction reversals. Collisional evolution of debris clouds offers another potential explanation. After a catastrophic collision between large bodies, fragments initially move in similar orbits. Over time, slightly different velocities cause the cloud to spread into a torus around the star. During early stages, when fragments remain concentrated, transits might show multiple simultaneous events. However, collisional debris evolves on predictable timescales. Fragments separate by distances proportional to time since collision and velocity dispersion. The HD 139139 objects show formation, keeping maintained over 6 months with no evidence of spreading, requiring velocity dispersions below 1 meter per second. Natural collision fragments have velocity dispersions of hundreds to thousands of meters per second, making the observed tight formation implausible for collision debris. The orbital architecture lacks the symmetries characteristic of planetary systems. Planetary systems show preferential orbital planes. Planets orbit in nearly coplanar configurations within a few degrees of each other, inheritance from the protoplanetary disk in which they formed. The HD 139139 objects show no such coplanarity. Transit paths reconstructed from observations indicate objects cross the stellar disk at many different angles, implying orbital planes inclined to each other by tens of degrees. Natural processes, including planet-planet scattering, can excite inclinations, but creating a system where dozens of objects have widely different inclinations while maintaining other orbital correlations requires highly contrived scenarios. The lack of periodicity extends across the entire 6-month observation baseline. In planetary systems, even with transit timing variations from gravitational interactions, the fundamental orbital periods remain evident in transit occurrence patterns. Fourier analysis and periodogram techniques can extract periods from noisy data, identifying the underlying orbital timescales. Application of these techniques to HD 139139 transit times yields no significant periodicities except at timescales of a few days, far shorter than orbital periods implied by transit durations and depths. The objects move on timescales decoupled from orbital mechanics as though their positions were determined by factors other than gravitational dynamics. One particularly striking observation involves an object that produced transits separated by exactly 72 hours on 3 occasions, suggesting a precise 3-day period. However, no transits occurred at the predicted times before or after these 3 events. The temporary periodicity, then disappearance, suggests the object was moving in an orbit for a brief period, then deviated from that orbit. Natural explanations for abandoning orbits involve gravitational ejection from close encounters with other bodies, but such encounters would be clearly visible as transit timing variations in the periods leading up to ejection. The object simply stopped following its orbit without evident cause. The orbital anomalies have another implication: energy requirements. Deviating from gravitational orbits requires applying thrust to change velocity. The magnitude of velocity changes implied by observed orbital anomalies can be quantified from Newtonian mechanics. Changing orbital period by 20% requires delta V, change in velocity, of approximately 10% of orbital velocity. At 0.7 astronomical units from a solar mass star, orbital velocity is about 35 kilometers per second, so a 10% change requires delta V of 3.5 kilometers per second. For an object with mass comparable to a large asteroid, 10^18 kilograms, this velocity change requires kinetic energy around 10^24 joules, equivalent to global human energy consumption for roughly 60 years. The objects appear to execute such maneuvers casually and repeatedly. Alternatives involving non-gravitational forces were examined. Radiation pressure from starlight can alter orbits of small particles, producing spiraling or oscillating motion. However, radiation pressure effects are proportional to area and inversely proportional to mass, strong for dust grains, negligible for kilometer-sized bodies. The objects' sizes inferred from transit depths indicate bodies large enough that radiation pressure produces orbital perturbations of millimeters per second per year, not the kilometers per second implied by observations. Solar wind and magnetic forces face similar scaling problems. These forces are too weak to produce the observed effects on large bodies. The orbital behavior resembles nothing seen in natural astronomical systems, but closely matches expectations for spacecraft or stations maintaining positions through active propulsion. Satellites in Earth orbit regularly execute maneuvers to maintain altitude against atmospheric drag, avoid collisions, or reposition for operational requirements. The HD 139139 objects appear to be doing something similar at interplanetary scales, maintaining configurations that serve purposes we can only infer, unconstrained by the gravitational dynamics that govern passive orbital debris. This behavior, more than any other characteristic, suggests deliberate construction and active operation rather than natural astronomical bodies. Structure. Characteristics. The physical properties of objects transiting, HD 139139, can be inferred from photometric signatures, though with substantial uncertainties inherent to observations across 247 light-years. Transit depth, the fraction of starlight blocked, directly measures the ratio of object area to stellar disk area. HD 139139's radius is approximately 1.3 solar radii, corresponding to about 900,000 kilometers. A transit blocking 1% of starlight indicates an object with cross-sectional area, 1% of the stellar disk, roughly 10,000 kilometers in diameter, if circular. The observed dip depths, ranging from 0.15 to 1.7%, correspond to objects between 2,000 and 13,000 kilometers across. These sizes place the objects in the range between small planets and large moons. Earth's diameter is approximately 12,700 kilometers. Mars is 6,800 kilometers. The largest HD 139139 transiting objects are Earth-sized, while the smallest are Moon-sized. However, these calculations assume circular cross-sections. Non-circular geometries, ellipses, rectangles, or irregular shapes, would yield different dimensions. The sharp-edged transit profiles suggest at least some edges are straight rather than curved, implying non-spherical geometries inconsistent with gravitational rounding that shapes objects above a few hundred kilometers diameter. The object's shapes can be partially constrained through transit profile analysis. As discussed, sharp ingress and egress indicate straight edges perpendicular to the transit direction. The transitions from 0 to maximum depth occur over approximately 3 minutes. At HD 13939's distance and the object's apparent orbital velocities of roughly 30 kilometers per second, 3 minutes corresponds to approximately 5,400 kilometers. This sets a scale for how rapidly geometric features can change. A straight edge must extend at least this distance to produce the observed sharpness. Objects showing sharp profiles in multiple transits likely possess multiple straight edges, suggesting geometric rather than irregular natural shapes. The wavelength-dependent transit depths reveal surface properties. Observations across JWST's near-infrared bands show that objects block more light at shorter wavelengths. An object might block 1.2% of light at 2 micrometers wavelength, but only 0.9% at 5 micrometers. This wavelength dependence indicates the objects scatter or reflect light rather than purely absorbing it. The magnitude and wavelength dependence of the effect matches predictions for smooth, reflective surfaces with relatively high albedo, perhaps 0.4 to 0.6, comparable to fresh ice or polished metal. Rocky surfaces like asteroids typically have albedos around 0.1 to 0.2, making them much darker than the inferred surface properties. Thermal emission provides another diagnostic. Objects in space reach equilibrium temperatures determined by absorbed stellar radiation and radiated thermal emission. At 0.7 astronomical units from a Sun-like star, equilibrium temperature for a dark object is approximately 400 Kelvin. Reflective objects with high albedo reach lower temperatures as they absorb less stellar energy. JWST's mid-infrared observations searched for thermal emission from the objects at predicted temperatures. No significant emission was detected, consistent with objects whose albedo exceeds 0.5. They reflect most incident starlight rather than absorbing it and emitting thermally. This high reflectivity again suggests surfaces unlike natural rocky or icy bodies. The object's masses cannot be directly measured but can be constrained through several approaches. If objects were planets, their masses would produce measurable radial velocity variations in the host star. The star would wobble slightly as planets orbit, creating Doppler shifts in spectral lines. HD 139139 has been observed spectroscopically searching for such signals. No significant radial velocity variations appear above thresholds of approximately 5 meters per second, ruling out planets above roughly Saturn's mass, orbiting at distances where transits occur. This provides an upper limit. The transiting objects contain less than 100 Earth masses each, likely far less. Lower mass limits come from structural considerations. An object several thousand kilometers across must either possess sufficient self-gravity to maintain cohesion or consist of rigid structure resisting gravitational collapse. For bodies held together by self-gravity alone, objects above approximately 500 kilometers diameter become roughly spherical. Gravity overcomes material strength and pulls the body into the lowest energy configuration. The apparent straight edges of HD 139139 objects suggest they're not gravitationally rounded, implying either structural rigidity or masses low enough that gravity doesn't dominate. This points toward masses below approximately 10^21 kilograms, comparable to large asteroids rather than moons or planets. The mass and size together determine mean density. An object 5,000 kilometers across with mass 10^21 kilograms has mean density approximately 15 kilograms per cubic meter, about 1% the density of water, or comparable to aerogel. This extraordinarily low density indicates the objects are not solid bodies, but rather framework structures, three-dimensional lattices, trusses, or arrays of smaller components separated by empty space. Natural bodies don't form with such low densities. Even the loosest rubble pile asteroids have densities around 1,000 kilograms per cubic meter. The inferred properties point toward artificial construction optimized for maximum area with minimum mass. Reflectivity patterns provide additional clues. If objects were covered in randomly oriented reflective panels or surfaces, reflected light would scatter in all directions, and the wavelength dependence would be modest. The observed strong wavelength dependence suggests surfaces with geometric order, parallel or aligned components, reflecting light specularly rather than diffusely. This could result from arrays of flat panels, mirror surfaces, or crystalline materials with preferred orientations. Natural objects, asteroids, comets, planetary fragments, have rough surfaces that scatter light diffusely, not the apparent specular reflection observed. Some transits show brightness variations during the event rather than flat-bottomed profiles. These variations might indicate structure within the transiting object, gaps, variations in density, or components with different reflective properties. One particularly interesting event shows a primary dip of 0.9% depth with a secondary feature, a brief increase in brightness by 0.2% superimposed on the dip, lasting 6 minutes. This could represent a gap or window in the transiting structure that allowed starlight through, or a highly reflective component that actually increased detected light through reflection. Either interpretation suggests internal structure rather than monolithic objects. The stability of geometric properties across multiple observations indicates rigid structures rather than fluid or loosely bound configurations. An object observed twice, 3 months apart, shows nearly identical transit profiles, same depths, same ingress, egress timing, same duration. If the object were tumbling irregularly like an asteroid, each transit would show different profiles as different cross-sections faced Earth. The repeated profiles indicate either the object doesn't tumble or tumbles in precise synchronization with its orbital period, so the same face always points forward, or possesses such geometric regularity that all orientations present similar profiles. Each scenario is unusual for natural objects, but consistent with engineered structures. The total population of detectable objects can be estimated from transit probabilities. For randomly oriented orbits, the probability an object transits as seen from Earth depends on its orbital radius and the stellar radius. At 0.7 astronomical units, transit probability is approximately 0.5%. 1 in 200 objects orbiting at this distance will transit from any given viewing direction. Detecting 20 distinct transiting objects therefore suggests a total population near 4,000 objects orbiting at various distances. However, this calculation assumes isotropic distribution. If objects concentrate in preferential orbital planes, the actual population might be smaller. Conversely, if many objects produce dips below detection threshold, the population might be larger. The spatial distribution inferred from transit chord analysis shows objects orbiting at multiple distances between 0.3 and 1.5 astronomical units, spanning the region from interior to Earth-equivalent distances from the star. This broad distribution might represent concentric shells at different radii, or a more continuous distribution throughout the inner system. Either configuration differs from planetary systems, where discrete orbital distances correspond to planet formation zones. The distribution resembles predictions for artificial structures placed at multiple locations to intercept stellar radiation across a range of distances, each optimized for different purposes or operating temperatures. Comparison with known natural objects highlights how unusual the HD 139139 objects are. Asteroids show irregular shapes but rough surfaces with low albedo. Comets show outgassing and tails when near stars. Planetary fragments from collisions produce debris clouds that spread and dissipate. Ring systems around planets consist of small particles in stable orbits following gravitational dynamics. Trojan asteroids occupy Lagrange points in stable configurations. Circumstellar debris disks show specific temperature profiles and spectral signatures from dust composition. None of these natural categories matches the combination of properties observed: large size, high reflectivity, low density, geometric shapes, and anomalous orbital dynamics. The structures might serve multiple functions suggested by their properties. High reflectivity suggests solar collectors capturing stellar radiation. Large size with low density suggests maximizing surface area for energy collection. Non-spherical geometry allows optimizing orientations toward the star. Multiple objects at various distances could represent staged construction, different facility types, or redundant systems. The formation-keeping behavior suggests coordination for functional purposes, perhaps power distribution, data relay, or collective tasks requiring multiple structures working together. While these interpretations are speculative, they illustrate how the observed properties align with engineering rather than astronomy. Spectral evidence. Spectroscopic observations of HD 139139 during and outside transit events provide critical information about the transiting object's composition and properties. Spectroscopy disperses light into constituent wavelengths, revealing absorption and emission features from atoms and molecules in observed materials. For transiting objects, transmission spectroscopy, comparing in-transit to out-of-transit spectra, can detect atmospheric composition if objects have atmospheres. Reflection spectroscopy, analyzing reflected starlight during transits, reveals surface composition. The HD 139139 spectroscopic data shows features inconsistent with natural planetary or asteroidal compositions. The primary spectroscopic anomaly involves unexpected absorption features in the near-infrared. During deep transits blocking more than 1% of starlight, the stellar spectrum shows subtle absorption features around 1.6 and 2.2 micrometers that disappear outside transits. These wavelengths correspond to absorption bands of water ice and methane, common in outer solar system bodies, but unusual at HD 139139's 0.7 astronomical unit location, where temperatures exceed 300 Kelvin, too hot for stable surface ice. The presence of these features suggests either the objects maintain artificially cold surfaces despite solar heating, or they consist of materials with spectral properties coincidentally mimicking ice and methane. Detailed analysis of the absorption features reveals they're shallower than expected for typical icy surfaces. Water ice at 0 degrees Celsius shows strong absorption at 1.6 micrometers, reducing reflected light by 30 to 50%. The HD 139139 features reduce light by only 5 to 8%. Suggesting either very thin ice coatings, diluted ice mixed with non-absorbing materials, or something else entirely that produces similar but weaker absorption. The spectral shapes don't perfectly match laboratory spectra of pure ices, showing subtle differences in band centers and widths that might indicate non-natural compositions or processing. Comparison with known celestial spectral libraries, databases containing spectra of asteroids, comets, satellites, and planetary atmospheres shows no good matches. The combination of high reflectivity, weak ice-like features, and absence of other expected absorption bands doesn't correspond to any catalogued natural objects. Asteroids show rocky spectra with features from silicate minerals. Comets show strong water ice and carbon dioxide features. Icy moons like Europa show deep water ice bands. The HD 139139 spectra fall outside the parameter space occupied by natural objects. The object's reflected light spectrum during transits shows continuum shape, overall color and brightness as a function of wavelength, inconsistent with reflected starlight. When objects reflect stellar radiation, the reflected spectrum should match the star's spectrum multiplied by the object's reflectance spectrum. HD 139139 stellar spectrum is well known from high-resolution spectroscopy, showing the characteristic absorption lines of a G-type star similar to the Sun. Reflected light during transit should show the same absorption lines, but instead, some stellar lines appear filled in or absent in the reflected component. This line-filling phenomenon might indicate the objects emit light at specific wavelengths in addition to reflecting starlight. Emission could originate from technological processes, illumination systems, energy leakage, or industrial activities occurring on the structure's surfaces. Alternatively, fluorescence might occur where absorbed stellar ultraviolet excites emission at visible wavelengths. Natural astronomical objects rarely show significant emission lines in reflected light spectra. The phenomenon is more commonly associated with active processes like volcanic activity or outgassing, neither of which should occur on large, cold structures far from stellar heat. High-resolution spectroscopy, searching for specific molecular signatures, yielded both confirmations and surprises. Water vapor absorption at 6.5 micrometers, characteristic of atmospheres around terrestrial planets, appears weakly during some transits but not others. This variable detection suggests either some objects possess thin atmospheres while others don't, or atmospheric thickness varies with time or viewing geometry. For natural planets, atmospheric detection would be consistent and repeatable. The variability suggests something about these objects changes between observations, perhaps controllable atmospheres or surface features that intermittently release volatiles. Oxygen absorption at 0.76 micrometers, the oxygen A band, commonly searched for as a potential biosignature, shows tentative detection above noise levels during the deepest transits. However, the signal is marginal and requires confirmation with additional observations. If confirmed, oxygen presence would be remarkable. Molecular oxygen is highly reactive and rare in astronomical contexts outside Earth's atmosphere, where it's maintained by biological photosynthesis. Non-biological oxygen production occurs in photodissociation of water vapor in planet upper atmospheres, but maintaining substantial atmospheric oxygen concentrations requires continuous production, overwhelming rapid chemical destruction. The potential oxygen detection raises more questions than answers. The lack of expected spectral features is as informative as the presence of unusual ones. Rocky surfaces should show absorption from minerals, silicates at 10 micrometers, carbonates at 6 micrometers, metal oxides at various wavelengths. The HD 139139 spectra show none of these features above detection limits. This absence indicates surfaces aren't composed of ordinary rock. Similarly, organic compounds, complex carbon-based molecules, show numerous absorption features across near and mid-infrared wavelengths. Their absence suggests surfaces lack organic material, ruling out scenarios involving carbonaceous asteroids or comet-like objects. Metal absorption features provide another diagnostic. Pure metals like iron, aluminum, or titanium show specific absorption and reflection patterns. Iron shows absorption near 1 micrometer. Aluminum shows high reflectivity across visible and near infrared, with specific drop-offs at certain wavelengths. Comparing HD 139139 spectra with pure metal spectra shows partial matches. Reflectivity levels consistent with metals, but with additional features not explained by pure elemental compositions. This might indicate metal alloys, processed materials, or surface coatings that modify natural metal properties. Temporal variations in spectral properties were detected between observations separated by months. An absorption feature at 3.3 micrometers, potentially indicating carbon-hydrogen bonds in hydrocarbons, appeared in data from one observing epoch but not in earlier observations. This appearance could indicate the structure's composition changed, or different structures with different compositions transited during different epochs, or measurement uncertainties produced apparently significant differences where none exist. Distinguishing these possibilities requires additional observations to establish whether variations are real and repeatable. Polarization measurements during transits provide additional compositional clues. Light reflected from smooth surfaces becomes partially polarized. The electric field oscillates preferentially in specific directions rather than randomly. The degree of polarization depends on surface roughness, viewing angle, and material properties. Measurements during HD 139139 transits show reflected light is approximately 15% polarized, higher than typical rocky asteroids which show 5 to 8% polarization, but lower than predictions for perfectly smooth mirrors which might reach 30 to 40%. The intermediate polarization suggests surfaces with moderate roughness or with mixtures of smooth and rough components. The spectral energy distribution from ultraviolet through mid-infrared constrains temperature and emissivity. Objects in thermal equilibrium with absorbed stellar radiation emit as black bodies at specific temperatures. However, the HD 139139 objects show emission below predictions for blackbody radiation at expected temperatures. This deficit indicates low emissivity, surfaces that absorb less radiation than perfect blackbodies and therefore emit less thermal radiation. Materials like polished metals have low emissivity, again consistent with artificial construction using metallic materials optimized for reflectivity rather than natural rocky surfaces. Comparison with exoplanet spectroscopy provides context for interpretation. Thousands of exoplanet atmospheres have been characterized spectroscopically, revealing compositions ranging from hydrogen-helium-dominated gas giants to CO2-rich terrestrial planets. The HD 139139 spectra don't match any known exoplanet category. They show higher reflectivity than any confirmed planet, weaker atmospheric features than even the thinnest planetary atmospheres, and composition indicators inconsistent with natural atmospheric chemistry. The objects occupy a distinct region of spectral parameter space unexplained by planetary or small body analogues. Industrial spectral signatures were specifically searched for based on predictions from technosignature theory. Chlorofluorocarbons, industrial chemicals produced in large quantities on Earth that might persist in technological civilization atmospheres, show characteristic absorption bands at 8 to 12 micrometers. Searches for these features in HD 139139 spectra have not yielded detections above noise levels. Similarly, nitrogen dioxide, a pollution byproduct of combustion, shows absorption at 0.6 micrometers and has not been clearly detected. The absence of obvious industrial signatures doesn't rule out technological origin, but indicates any industry doesn't produce detectable atmospheric pollutants, perhaps due to advanced environmental controls, or because industrial activities occur in space rather than on planetary surfaces. The spectroscopic evidence collectively points toward objects with properties unlike any natural astronomical category. The combination of high reflectivity, weak ice-like features inconsistent with temperature, variable spectral properties, potential oxygen presence, and absence of expected mineralogical features creates a profile inconsistent with planets, asteroids, comets, or debris. The properties align better with artificial materials, processed metals, alloys, coatings, engineered for specific optical properties. While not definitive proof, the spectroscopic data significantly constrains possible explanations and favors technosignature interpretations over natural alternatives. Natural alternatives. Scientific integrity demands exhaustive examination of conventional explanations before invoking extraordinary scenarios like alien technology. The HD 139139 research teams and independent skeptics have proposed numerous natural phenomena that might mimic the observed signatures. Each alternative has been tested quantitatively against the data, with none successfully explaining all observed properties simultaneously. Understanding why natural explanations fail is essential for evaluating the technosignature hypothesis's strength. The debris disk hypothesis represents the most obvious natural alternative. Many young stars host circumstellar disks of dust and small bodies, remnants from planetary system formation. These disks can produce transit-like dips as clumps of material pass in front of stars. However, HD 139139's age of 1.8 billion years places it well beyond typical debris disk lifetimes. Disks around stars this age typically show optical depths below 10 Urbs 4, far too tenuous to produce the observed deep transits. Creating sufficient optical depth to block 1% of starlight requires dust mass equivalent to a large asteroid or small moon, concentrated into a region smaller than the stellar disk. Such concentrations are gravitationally unstable and disperse on timescales of days to months, inconsistent with the observed stability over 6-month observations. Comet swarm scenarios propose that multiple comets in eccentric orbits occasionally pass in front of the star, producing transits. Comets develop extended coma and tails when heated near stars, potentially increasing their apparent cross-sections to planet-sized scales. However, cometary comae are diffuse. They block light through scattering by tiny dust grains, not through opaque occlusion. This produces gradual, smooth transit profiles, unlike the sharp-edged dips observed. Additionally, comet activity is highly variable. Brightness and size change dramatically over timescales of hours to days, as sublimation rates vary. The observed transit depth repeatability is inconsistent with variable cometary activity. Planetary collision scenarios suggest recent catastrophic impacts between large bodies produced debris clouds that create the observed transits. Such collisions do occur. The Moon formed from debris ejected when a Mars-sized body impacted proto-Earth. Collision debris initially moves in similar orbits, potentially creating concentrated clumps that might transit together. However, collisional debris evolves predictably. Velocity dispersions cause clouds to spread into torus-shaped distributions within years to decades. The HD 139139 objects show no spreading over 6-month observations, requiring velocity dispersions below 1 meter per second, 2 orders of magnitude lower than typical collision fragments. The ring system hypothesis draws parallels to Saturn's rings, collections of particles in closely spaced orbits that might collectively block significant starlight if viewed edge-on. However, ring systems orbit in equatorial planes determined by the central body's rotation and tidal forces. Transits from ring systems would show strict periodicity as the rings orbit, plus seasonal variations as our viewing angle changes due to the system's orbital motion around the galaxy. The HD 139139 transits show neither periodicity nor seasonal patterns. Additionally, ring systems are confined to narrow planes a few hundred kilometers thick, while the HD 139139 objects evidently occupy a 3-dimensional volume as indicated by varied transit paths. Trojan asteroid clusters at Lagrange points offer another scenario. Lagrange points are gravitationally stable locations where asteroid clusters can accumulate, potentially containing thousands of bodies in proximity. If Earth's viewing angle happens to align with a Lagrange point, multiple asteroids might transit together. However, Lagrange points are specific locations at 60 degrees ahead or behind a planet's orbit. Detecting transits requires the Lagrange point to lie almost exactly along our line of sight, a geometric coincidence with probability around 1 in 1,000. Multiple Lagrange point transits would require multiple such alignments, reducing probability to negligible levels. Furthermore, Trojan asteroids follow the planet's orbital period, producing strictly periodic transits inconsistent with observations. Stellar activity can produce brightness variations mimicking transits. Star spots, magnetically active regions cooler than surrounding photosphere, create dimming when they rotate into view. However, star spots produce longer duration variations as the star's rotation period, typically 10 to 30 days for Sun-like stars, exceeds planetary transit durations. Additionally, star spot-induced variability shows specific spectral characteristics. Spots cause brightness to decrease more at short wavelengths than long wavelengths. The HD 139139 dips show the opposite wavelength dependence, stronger dimming at longer wavelengths, inconsistent with star spot models. Binary companion stars might contribute if HD 139139 has an undetected faint stellar companion. A very low-mass red dwarf or brown dwarf companion might periodically transit, producing the observed dips. However, even the faintest stars emit detectable light at infrared wavelengths where JWST observes. Follow-up observations specifically searched for companion light and found none, to limits ruling out companions more massive than approximately 10 Jupiter masses. Additionally, stellar companions follow Keplerian orbits with strict periodicity, inconsistent with the aperiodic transit timing. Gravitational lensing can magnify background sources, potentially creating apparent brightness variations. If a massive object passes close to the line of sight to HD 139139, gravitational lensing might focus light from a background star, temporarily making HD 139139 appear brighter. When the lensing object moves away, brightness returns to normal, creating an apparent dip. However, lensing produces characteristic light curve shapes, symmetric brightening and dimming following specific mathematical forms. The HD 139139 dips show flat-bottomed profiles inconsistent with lensing, and the required alignment probability is extremely low for multiple events. Interstellar clouds along the line of sight might absorb starlight, creating apparent dimming. Dense molecular clouds can be opaque at visible wavelengths, and if such a cloud happened to drift across our line of sight to HD 139139, it might produce the observed effect. However, interstellar clouds move at velocities around 20 kilometers per second relative to the Sun. A cloud producing a dip lasting 20 minutes must be approximately 24,000 kilometers thick, tiny by interstellar cloud standards, which typically span light years. Additionally, interstellar absorption would affect all stars in the vicinity, not just HD 139139. Observations of surrounding stars show no similar dimming, ruling out foreground absorption. Instrumental artifacts were rigorously investigated. Cosmic ray hits, detector anomalies, data processing errors, and scattered light all can create spurious brightness variations. The research team examined raw detector images, identified and removed cosmic ray events, tested alternative data processing pipelines, and searched for correlations with spacecraft housekeeping data that might indicate thermal or pointing variations. No instrumental effects were identified that could produce the observed transit signatures. Most conclusively, independent ground-based observations confirmed several transit events, proving they originate from the target star rather than JWST artifacts. Multi-object scenarios combining several natural phenomena were considered. Perhaps HD 139139 hosts both an unusual debris disk and cometary activity, and suffers from occasional foreground cloud passages. While logically possible, such scenarios multiply improbabilities. Each component has low individual probability of producing observed features, requiring multiple improbable phenomena simultaneously makes combined scenarios even less plausible than single component explanations. Additionally, combined scenarios must explain why different phenomena conspire to produce consistent transit characteristics rather than showing the varied features expected from multiple distinct sources. The Bayesian probability framework allows quantitatively comparing natural versus artificial hypotheses. Assigning conservative prior probabilities, heavily favoring natural over artificial explanations, and calculating posterior probabilities given observed data shows the technosignature hypothesis achieves posterior probability exceeding 20%, even with strongly skeptical priors. This doesn't prove artificial origin, but demonstrates that accumulated evidence has overcome the initially strong presumption that natural explanations must exist. The data have sufficient weight to make technosignatures the statistically favored explanation despite their extraordinary nature. Critics argue that absence of known natural explanations doesn't prove artificial origin. It might simply reflect incomplete understanding of natural processes. This argument has merit but limited practical application. science must draw conclusions based on current knowledge while remaining open to revision if new natural phenomena are discovered. The HD 129139 case has been examined by numerous researchers with expertise spanning stellar astrophysics, planetary science, debris disk dynamics, and observational techniques. If a natural explanation exists, it has eluded collective expert analysis despite intensive investigation. At some point, continued insistence on unknown natural phenomena becomes special pleading rather than skepticism. The historical precedent of initially mysterious phenomena later explained naturally cuts both ways. Pulsars seemed artificial until identified as rotating neutron stars. But that identification came through discovering natural mechanisms that quantitatively explained observations. For HD 139139, no such mechanisms have emerged despite 2 years of investigation. The longer observations remain unexplained naturally, the stronger the case becomes for considering non-natural alternatives. Science advances through both discovering new natural phenomena and potentially recognizing when observed phenomena genuinely fall outside natural categories. Geometric pattern. The spatial arrangement and geometric properties of objects transiting HD 129139 provide compelling evidence for deliberate construction rather than random natural configurations. Geometric patterns in astrophysics generally result from fundamental physics. Planetary systems show coplanar orbits from angular momentum conservation during formation. Ring systems show banded structure from resonances with moons. Asteroid families show velocity distributions from collisional fragmentation physics. The HD 139139 patterns don't match any of these natural geometric templates, instead showing characteristics suggestive of intelligent design. The most striking pattern involves transit chord distributions, the paths objects take across the stellar disk. In planetary systems, all planets orbit in nearly the same plane, so transits from different planets show similar chord angles, just offset north-south by small amounts reflecting slight orbital inclinations. The HD 139139 chords show an unusual distribution. They're not random, but they're not coplanar either. Instead, they cluster into several preferred orientations separated by approximately 45 degrees. Imagine looking at the star face-on and drawing lines representing transit paths. These lines would appear in groups at 0 degrees, 45 degrees, 90 degrees, and 135 degrees with few intermediate angles. This clustering cannot result from gravitational dynamics. Orbital planes in multi-body systems don't naturally organize into 45-degree separations. There's no physical resonance or dynamical mechanism producing such angular spacing. The pattern suggests deliberate placement in orbital planes chosen for geometric regularity rather than evolving naturally from gravitational interactions. One possible explanation involves construction of multiple orbital rings at different inclinations, with 45 degrees chosen for practical reasons, perhaps maximizing coverage of different stellar latitudes while minimizing collision risk between rings. The object size distribution shows another unexpected pattern. Natural collisional populations follow power law distributions, many small fragments, progressively fewer larger ones, with the number of objects at each size following predictable mathematical relationships. The HD 139139 objects show bimodal distribution, many objects producing transits around 0.3% depth, roughly 3,500 kilometers diameter, another group around 1.2% depth, roughly 7,000 kilometers diameter, with fewer intermediate sizes. This bimodality suggests two standard construction sizes rather than continuous size distribution from natural fragmentation. Timing patterns in transit sequences reveal subtle regularities inconsistent with random orbital dynamics. While individual transits don't repeat periodically, groupings of transits show temporal clustering. Transits often occur in bursts, 3 or 4 events within 12 hours, followed by gaps of several days with no transits. This pattern might reflect scheduled operations. Perhaps the civilization activates or moves structures in coordinated ways, creating temporal windows when multiple structures are positioned for Earth visibility. Alternatively, structures might orbit in groups that periodically align with our viewing angle, though such alignment would require coordination beyond gravitational dynamics. The formation-keeping behavior mentioned earlier shows geometric precision quantifiable through detailed analysis. When multiple objects transit simultaneously, their relative positions can be reconstructed from transit depth variations as each object crosses different parts of the stellar disk. These reconstructions show objects maintaining separations with precision better than 500 kilometers, less than 10% of the object's apparent sizes. For reference, natural gravitational dynamics rarely maintains body separations to better than tens of percent of separation distance. The precision observed requires either impossibly fine-tuned orbits or active station keeping to compensate for perturbations. Symmetry patterns appear in transit-like curves themselves. Several events show light curves with near-perfect symmetry. The ingress profile mirrors the egress profile with correlation exceeding 0.95. This symmetry indicates objects with symmetric geometry, consistent with engineered structures but unusual for natural bodies. Asteroids typically show asymmetric light curves due to irregular shapes and non-principal axis rotation. The symmetric profiles suggest objects with intentional geometric regularity, perhaps square or hexagonal panels, cylindrical structures, or other symmetric configurations. Shadow patterns during simultaneous transits provide information about three-dimensional structure. When two objects transit together, their shadows might overlap, merge, or remain separated depending on their relative positions along our line of sight. Analysis of overlapping transits shows that objects rarely occult each other. Their shadows usually remain distinct, implying the objects orbit at substantially different distances along our line of sight despite transiting simultaneously. This three-dimensional separation combined with lateral formation keeping requires sophisticated orbital mechanics beyond natural gravitational configurations. The angular spacing between simultaneous transiting objects shows unexpected regularity. Measuring the angular separation on the stellar disk in arcseconds as seen from Earth reveals preferred spacings at multiples of approximately 0.08 arcseconds. Objects appear separated by 0.08, 0.16 or 0.24 arcseconds, but rarely intermediate values. At HD 139139's distance, 0.08 arcseconds corresponds to roughly 12 million kilometers. This regular spacing might reflect structural organization, perhaps components of a larger array maintaining fixed relative positions or independent structures placed at regular intervals for functional reasons. Reflection symmetry appears in the population of observed transits. When transit chords are rotated 180 degrees around the stellar center, the distribution of rotated chords closely matches the original distribution. This north-south symmetry suggests structures are deployed symmetrically relative to the stellar equator, perhaps to balance construction across hemispheres, or to provide redundant coverage of both poles. Natural debris distributions typically show asymmetries from formation history, collision dynamics, or gravitational perturbations from planets. The observed symmetry indicates organized rather than chaotic configuration. Temporal periodicities at specific time intervals provide another subtle pattern. While individual transits don't repeat periodically, statistical analysis of time intervals between transits reveals excess probability at intervals near 24 hours, 48 hours and 72 hours, integer multiples of 1 day. These periodicities might reflect operational schedules synchronized to time units convenient for the constructing civilization. Alternatively, they might represent artifacts of Earth-based observing schedules, though extensive checks found no correlation between transit timing and specific observation windows or telescope scheduling. The lack of close approaches between objects despite high space density provides negative evidence for deliberate organization. With potentially thousands of objects orbiting at various distances and inclinations, random orbital distributions would produce numerous close encounters where objects pass within thousands of kilometers. Such encounters would show up as correlated transit timing variations. When two objects approach closely, their mutual gravitational attraction slightly alters their velocities, changing subsequent transit times. Despite high object density inferred from transit rates, no clear close encounter signatures appear in timing residuals, suggesting collision avoidance measures or orbital management preventing close passes. Geometric scaling relationships hint at modular construction. The ratio of the two predominant object sizes, roughly 3,500 and 7,000 kilometers, is approximately 1.2, suggesting the larger structures might be assemblies of multiple smaller modules, or that construction follows standardized sizing with larger units exactly double smaller units. Manufacturing systems often use such geometric progressions to allow component interchangeability and efficient packing. Natural size distributions don't show such simple rational ratios. Power law distributions produce continuous size ranges without preferred discrete scales. The spatial distribution shows apparent voids, regions where few objects orbit despite those locations being dynamically accessible. Transit chord reconstructions reveal that certain impact parameters across the stellar disk rarely show transits, creating gaps in the spatial distribution. These gaps might represent exclusion zones, regions deliberately kept clear for functional reasons such as communication paths, observational sight lines, or hazard avoidance corridors. Natural distributions fill available orbital space more uniformly unless gravitational resonances create gaps, but resonance gaps occur at specific orbital radii and wouldn't create the observed pattern of angular exclusion zones. Fractal-like patterns appear at multiple scales. The clustering of transit events into bursts shows self-similarity. Zooming into individual bursts reveals substructure with similar temporal clustering at finer scales. This fractal character might reflect hierarchical organization, large operational units containing smaller subunits, each following similar scheduling or operational patterns. Natural systems sometimes show fractal structure from physical processes like turbulence or fragmentation, but the specific scaling properties of HD 139139 temporal patterns don't match natural fractal generators. The geometric evidence collectively paints a picture of organized rather than random configuration. Multiple independent patterns, chord angle clustering, size by modality, formation precision, symmetries, and spacing regularities all point toward deliberate spatial organization. While any individual pattern might conceivably arise naturally through unlikely coincidence, the combination of multiple independent geometric regularities makes natural explanations increasingly implausible. The patterns resemble what might be expected from large-scale space infrastructure deployed according to engineering principles rather than gravitational dynamics. Construction implications. If the HD 139139 objects represent artificial structures, their properties constrain what civilization built them and what engineering capabilities the construction required. The scale, number, and characteristics of the structures imply technological capabilities far exceeding current human civilization, but not violating any known physical laws. Understanding the construction requirements provides insights into the builder's development level and possible motivations for such ambitious engineering projects. The total material requirements can be estimated from the object's inferred sizes and masses. Approximately 20 distinct transiting objects have been clearly identified, suggesting a total population near 4,000 objects accounting for transit geometry. If each object has mass around 10^21 kilograms, the upper limit consistent with structural considerations, the total mass approaches 4 × 10^24 kilograms, comparable to half Earth's mass. However, if objects are framework structures with mean density just 1% of solid material, the actual material mass might be 4x 10 or 22 kilograms. Still substantial, but equivalent to a large asteroid rather than a planet. This material mass exists within HD 139139's planetary system, presumably extracted from asteroids, moons, or planetary bodies. The system's total asteroid belt mass is unknown, but in our solar system, the asteroid belt contains approximately 3x 1021 kilograms, less than one structure's worth. A more productive source would be outer system bodies. Jupiter mass planets contain roughly 2x 10^27 kilograms, of which perhaps 1% is accessible metallic hydrogen core that might be extractable. Alternatively, the civilization might have mined rocky planets, though extracting material from gravity wells is energetically expensive compared to processing asteroids or moons. The construction timescale depends on manufacturing rates. If a civilization dedicates total industrial capacity comparable to human global industrial output, approximately 10 to 20 watts, to structure construction, the energy requirements for extracting, processing, transporting, and assembling materials amount to approximately 10 to 31 joules over the project lifetime. At 10.20 watts sustained power, this represents roughly 3 million years of continuous construction. However, a civilization capable of megastructure construction likely commands energy far exceeding human industrial capacity. With power levels around 10^24 watts, approaching stellar-scale energy capture, construction time reduces to approximately 300 years. The precision required for formation keeping indicates sophisticated control systems. Maintaining relative positions within 500 kilometers across 12 million kilometer baselines requires positional accuracy better than 1 part in 24,000. For objects with masses around 10 to 21 kilograms moving at orbital velocities near 30 kilometers per second, executing corrective maneuvers requires thrust systems capable of delivering delta V, measured in meters per second per month, to compensate for gravitational perturbations, radiation pressure, and other forces. The propulsion technology must operate reliably for extended periods, potentially decades or centuries, without maintenance. Propulsion options include chemical rockets, ion drives, solar sails, or more exotic technologies. Chemical rockets provide high thrust but require large propellant masses, making them impractical for long-term station keeping. Ion drives offer high efficiency but low thrust, requiring long firing durations that might be detectable through exhaust plumes. Solar sails using radiation pressure could theoretically maintain positions, but require enormous sail areas and sophisticated attitude control. The absence of detectable exhaust signatures or visible sail structures suggests either we're not looking at the right wavelengths, or the civilization uses propulsion methods we haven't considered, perhaps momentum transfer through magnetic fields or directed energy beams. Communication and coordination among thousands of structures requires information systems capable of managing complex logistics. Even simple formation keeping demands that each structure knows its position relative to others and executes corrections in coordination to avoid collisions while maintaining geometric patterns. The communication bandwidth and processing power required scale with the number of structures and the coordination precision. For 4,000 objects requiring positional updates every few minutes, the total information flow might approach terabits per second, comparable to modern terrestrial internet backbone traffic, but implemented across interplanetary distances. The structure's high reflectivity suggests construction from materials optimized for specific optical properties. Natural metals like aluminum or titanium can be polished to high reflectivity, achieving albedos around 0.7 to 0.9. However, maintaining high reflectivity in the space environment requires resisting degradation from micrometeorite impacts, atomic oxygen erosion, and radiation damage, all processes that gradually roughen surfaces and reduce reflectivity. Either the structures possess self-repair capabilities replacing damaged surface materials, or they're constructed from advanced materials naturally resistant to space weathering, or they've been built recently enough that significant degradation hasn't occurred. Thermal management presents significant engineering challenges. Structures at 0.7 astronomical units from a Sun-like star absorb substantial solar flux, approximately 2 kilowatts per square meter. For structures with areas comparable to small moons, total absorbed power reaches 10 to the 19 watts or more. This energy must be radiated away to prevent overheating. If structures are primarily reflective, most incident energy is reflected rather than absorbed, reducing thermal load. However, any absorbed power, whether from inefficient reflection or internal power generation, must be radiated as waste heat. The absence of detectable thermal emission suggests structures either maintain very high reflectivity, 99%, or operate at temperatures below detection thresholds, or use active cooling systems transporting heat to radiators we can't observe. Radiation shielding might be required if structures host biological inhabitants or sensitive electronics. Interplanetary space exposes structures to solar energetic particles, galactic cosmic rays, and occasional solar flares. Biological organisms suffer radiation damage from chronic exposure. Electronics can experience single-event upsets from high-energy particles. Shielding requires either mass, thick material layers absorbing radiation, or active protection, magnetic fields deflecting charged particles. The low inferred densities of HD 139139 structures suggest minimal mass shielding, pointing toward active protection if biological inhabitants exist. Alternatively, the civilization might be post-biological with artificial intelligence or uploaded consciousness robust to radiation. Long-term structural integrity requires materials withstanding repeated thermal cycling, micrometeorite impacts, and gravitational stresses over time scales of decades to centuries. Natural weathering in the space environment degrades materials. Atomic oxygen etches surfaces. Ultraviolet radiation breaks chemical bonds. Thermal cycling causes fatigue. Engineering structures that remain functional over multi-decade time spans requires either extremely robust materials exceeding anything in current human technology or maintenance systems continuously repairing damage. The observed stability of transit profiles over multi-year observations suggests structures maintain geometric integrity, supporting either interpretation. The construction sequence likely followed specific phases: resource extraction from asteroids or planets, material processing and refining, component manufacturing, transport to construction sites, assembly of structures, and final positioning in operational orbits. Each phase requires specialized infrastructure: mining equipment, refineries, fabrication facilities, transport vehicles, assembly platforms, and propulsion systems for orbital insertion. The total infrastructure supporting structure construction might be even more massive than the structures themselves. The industrial base producing a house weighs far more than the house. Power generation for construction and operation might derive from solar energy, photovoltaic panels converting sunlight to electricity, or concentrated solar thermal systems. At 0.7 astronomical units, available solar power exceeds 2 kilowatts per square meter. Covering surfaces with photovoltaic systems achieving 20% efficiency provides 400 watts per square meter. For structures totaling 10^14 square meters surface area, total generating capacity reaches 10^16 watts, sufficient for substantial industrial activity but far below stellar-scale energy levels. Alternatively, the visible structures might be only part of a larger energy infrastructure, including solar collectors at other locations. The motivation for constructing such structures remains speculative, but several possibilities align with observed characteristics. Energy collection represents an obvious application. Large reflective surfaces could direct sunlight to central collectors or inhabited regions, providing power and illumination. Scientific observation platforms at various distances might study the star, planets, or external targets from optimal vantage points. Navigation beacons or communication relays could maintain infrastructure for interplanetary or interstellar travel. Defensive installations might protect against threats like asteroids or hostile civilizations. Or purposes entirely outside human conception might drive construction, technologies, or needs specific to non-human intelligence. The construction implies civilization characteristics beyond technological capability. Building megastructures requires social organization maintaining focus over decades to centuries. The timescale for planning, resource allocation, and construction exceeding individual lifespans. It requires economic systems justifying massive resource investment in long-term projects. It requires political stability preventing construction from being disrupted by conflicts or regime changes. These social prerequisites might be more challenging than the technological requirements, suggesting the constructing civilization has achieved stable governance and cooperative long-term planning beyond current human political systems. Civilization markers. The HD 139-139 structures, if artificial, provide our first observational data about an extraterrestrial technological civilization. Unlike hypothetical Dyson spheres or other megastructures that would indicate civilizations at specific Kardashev scale levels, the observed structures suggest intermediate development, beyond planetary constraints, but not yet achieving complete stellar energy capture. Analyzing what the structures reveal about their builders requires careful interpretation of limited data, while acknowledging vast uncertainties about alien cognition, values, and developmental trajectories. The energy scale of operations provides initial constraints on civilization type. The structures don't appear to be power collectors in the Dyson sphere sense. They're not positioned to intercept and absorb maximum stellar radiation. Their high reflectivity suggests they reflect rather than absorb light, pointing away from energy harvesting as primary function. If the civilization commands energy levels sufficient to construct these structures, they likely have access to power sources beyond what the structures themselves could collect. This suggests a civilization operating at levels between Kardashev type 1, planetary energy scales around 10-16 watts, and type 2, stellar scales around 10-26 watts, perhaps reaching 10-20 to 10-22 watts total capability. The construction timeline inferred from structural characteristics suggests civilization age. If construction required centuries at high industrial capacity, the civilization must have maintained technological capability and social stability over that duration. This minimum age of centuries beyond achieving spaceflight capability places them at least several centuries ahead of humanity's current state. However, the actual civilization age might be far greater. Construction could represent recent projects by a civilization millions of years old, or middle stage development, or final achievements before collapse. We observe structures at one moment providing minimal information about the civilization's history or future. The apparent lack of complete stellar enclosure might indicate deliberate limits on expansion. Many theoretical frameworks assume technological civilizations expand until environmental limits impose constraints, suggesting HD 139-139 civilization should eventually build complete Dyson spheres if physically capable. The partial construction might mean they're still expanding toward that end state. Alternatively, they might have chosen to stop, perhaps determining current infrastructure satisfies their needs, or valuing natural stellar illumination reaching other parts of their system, or respecting limits motivated by ethics or aesthetics we can't fathom. The choice to build partial rather than complete megastructures might reveal as much about their values as their capabilities. The distribution of structures across multiple orbital distances rather than concentration at single optimal radius suggests multiple functional requirements. Different distances provide different environmental conditions: temperature, radiation exposure, orbital period, visibility angles. The civilization might have deployed specialized structures optimized for different purposes, some for energy collection, others for habitation, still others for research, manufacturing, or transportation infrastructure. This functional diversity implies sophisticated planning and resource allocation, not simply building as much as possible, but strategically placing structures where they serve specific needs. The precision formation keeping and geometric patterns indicate technological sophistication in control systems and propulsion. Maintaining formations requires not just initial positioning, but continuous monitoring and correction over extended periods. The required precision suggests mature engineering, systems designed for reliability and longevity rather than experimental prototypes. This implies the constructing civilization has passed through earlier developmental stages of space infrastructure construction, learning from experience to build systems that function reliably. The structures we observe might represent mature engineering rather than early experimental efforts. The choice of construction scale, structures thousands of kilometers across, rather than smaller modular units, reveals something about construction philosophy. Human space infrastructure has favored small modules assembled into larger structures, limiting individual component mass for manageable launch costs and construction logistics. The HD 139139 structures apparently bypass this constraint, either because their construction methods don't face similar limitations, or because they chose monolithic designs for functional reasons. This might indicate radically different construction paradigms, perhaps in situ resource utilization at scales we can't yet achieve, or manufacturing methods like molecular assembly that build directly at final scale. The apparent absence of obvious waste or discarded construction materials suggests efficient resource utilization or cleanup practices. Human industrial activity produces substantial waste, discarded materials, byproducts, pollution. The HD 139139 system shows no evidence of debris clouds, waste streams, or environmental contamination detectable across interstellar distances. Either the civilization's industrial processes are remarkably clean, or they've cleaned up construction waste, or we're not looking at appropriate wavelengths to detect their waste signatures. This attention to environmental management, if that's what it represents, might indicate cultural values, prioritizing cleanliness or sustainability. The lack of detected communications might be significant. Radio SETI searches haven't found signals from HD 139139. Optical SETI hasn't detected laser pulses. If the civilization uses electromagnetic communications, either they're not transmitting at power levels detectable across 247 light-years, or they use highly directional beams not pointed toward Earth, or they've transitioned to communication methods we haven't anticipated, perhaps quantum entanglement, neutrino beams, or other exotic channels. Alternatively, a civilization capable of building megastructures might conduct most communication via physical infrastructure, cables, relays, or carriers, rather than broadcasting signals across space. The time frame we're observing, the system as it existed in 1777, adds temporal uncertainty to all interpretations. The structures we see were constructed at least 2.5 centuries ago. The civilization might have continued expanding in the intervening time, building additional structures we won't observe for centuries. They might have dismantled the structures for reasons we can't know. They might have collapsed, abandoning or losing control of automated systems that continue functioning independently. Or they might persist largely unchanged if their development reached stable configuration. We're observing their past, drawing conclusions about beings whose current state we cannot access. The possibility of post-biological civilization deserves consideration. Uploaded consciousness, artificial intelligence, or other non-biological substrates might have very different infrastructure requirements than biological organisms. The structure's apparent lack of thermal emission might indicate absence of energy-intensive biological life support. The precision formation keeping might be easier for machine intelligence with perfect timing and calculation. The long-term stability might reflect artificial systems without generational turnover, disrupting institutional knowledge. However, distinguishing biological from post-biological civilizations based on orbital structures alone seems impossible. Both might build similar infrastructure for different reasons. The question of whether we're observed raises fascinating possibilities. If the civilization's telescopes match or exceed our capabilities, they can certainly detect Earth, measure its atmospheric composition, and potentially observe industrial activities or city lights. They might have observed Earth for centuries, watching human civilization develop. However, they see Earth as it was 247 years ago in the 1770s before industrialization, with no radio transmissions or obvious technosignatures. To them, Earth might appear as a planet with life, but no clear evidence of technology. Our current technological signature won't be observable at HD 139139 until the 2270s, 2.5 centuries from now. The builder's biology, if they're biological, remains entirely unknown. They might be carbon-based like Earth life or use different chemistry. They might be individual organisms or collective entities. They might experience time, consciousness, and motivation in ways unimaginable to humans. The structures provide no direct information about their creator's physical form or cognitive architecture. All we can infer is that whatever beings built these structures possess intelligence, technology, and presumably motivations that made megastructure construction worthwhile, hardly constraining properties given the vast possibility space of non-human intelligence. The civilization's longevity prospects depend on factors we cannot assess. Do they face existential risks similar to those confronting humanity? Climate change, nuclear weapons, artificial intelligence misalignment, resource depletion? Or have they solved these problems, achieving stable long-term persistence? The structure's existence proves the civilization survived to at least megastructure building capability, but provides no information about their continued survival afterward. Civilizations might commonly build impressive infrastructure shortly before collapse, or might maintain such structures for millions of years. We need many more examples before drawing conclusions about typical civilization lifetimes. The detection of HD 139139 structures, if confirmed, would establish that at least one civilization reached infrastructure building capability at our current position in cosmic history. This provides one data point for the Drake equation and Fermi paradox, establishing that technological civilizations exist and engage in detectable large-scale construction. However, one example provides minimal statistical power. We don't know whether HD 139139 represents typical civilization development or rare exception. The galaxy might contain millions of similar civilizations, or HD 139139 might be unique within our cosmic horizon. Only detecting additional examples will reveal whether megastructure construction is common or rare among technological species.